Welcome to the Australian Water School, the home of demand-driven industry-designed training for the global water sector.
Well, welcome everybody to this Australian Water School webinar. It's so good to have you all here. Coastal Modelling 101. This is going to be good. Mitchell, Michael, we're so glad to have you also. We want you to sit back, relax, get your coffee. This is a great way to do webinars. It's a fantastic way to do webinar. In fact, let's see who's here. Look at this. Unbelievable. Over 50 countries represented. It's terrific. We're going to have a great discussion, I reckon. All right, Mitchell, Michael, are you there? That's fantastic. Yes, they are. Wonderful. Hi, Michael. Hi, Mitchell. How are you today?
Yeah, good. Thanks, Trevor. And yeah, good
Thanks,
to be here. Hey, everyone.
It is today in your area of the world, is it? I think a lot of people are watching today. It's not today. It's like midnight or something. Where are you from, Michael?
In Brisbane.
Brisbane and Mitchell?
Yeah, same place, Brisbane, Australia.
That's the wonderful warm part of Australia called Queensland. That's fantastic.
That's right.
That's excellent. Yeah. Mitchell's going to be presenting. Michael's going to be doing the answering on the Q&A panel and clarifying any questions. Come on screen whenever you want. Michael, correct your colleague Mitchell whenever you feel like it, although he won't like that very much.
It's pretty standard.
Standard stuff. That's good. I don't think so. This is looking very non-standard the way I look at your PowerPoint, Mitchell. It's fantastic. Mitchell's an associate principal engineer and leads Two-Flow's software development, Two-Flow FV's software development, and Michael is the lead water quality development person within Two-Flow BMT, Australia's software business. So looking forward to this today. What else was I going to say? Oh yeah, that Two-Flow was awarded most innovative company of the year. Is that the way to say this? Is that the right way to say this?
In the Australian Financial Review, Most Innovative Companies 2020, we were awarded a place, yes, and Two-Flow was the content of our submission for that award.
Fantastic, a fantastic award, and shows what's been happening for Two-Flow BMT. All right, we had a poll. Wonderful. Should we look at that poll? Here we go. Thank everyone for sharing your responses on that poll. Did we expect commercial consulting contracting to be as high as it is? Yes, we did.
Yeah.
Coastal modeling's got to be high up on planning as well as consulting. Academics, any comments across these questions? Number 2, any experience?
I think they're pretty interesting results around the good spread of the experience of people, and that's great to see. Good level of mixture with the different models as well. Interesting that a lot of people have said none for the types of models that they've used coastal processing.
Well, in fact, that's the highest category of none's the highest category of what models have you used. Yeah, it is too. And just going back, that other question about how many years, the highest one is 5 to 10. So they're right in the middle of their careers. That's great, everybody. Thank you for that. Skip down to number 4. How important? Ongoing sustainable. Very important here. Yeah. That was definitely the biggest category.
And the last one's interesting as well in terms of what people want to investigate. The 2D currents and water levels being a key one, but a reasonably good spread across a lot of the different categories there. So
it highlights the diversity of coastal modelling and coastal understanding. Yeah.
Sediment transport's right behind 2D current water levels in what typically do you want to investigate. Tsunamis in there, of course. Yeah. Yeah. All right. Happy with that?
Yep.
And I think we've done enough to get ourselves rip-roaring ready, got the coffee in hand, and I can't wait to see how this is going. Mitchell, we're in your hands. Michael, you're going to be hammering away with Q&A. So right over to you, Mitchell.
Coastal Modelling 101, it's really an introduction to some of the coastal modelling that you can do. And yeah, it's really interesting to see the poll question there about a lot of people maybe haven't done any modelling before. So this should be right up your alley, this presentation. So that's quite good. Today, I'm going to talk about coastal modelling and compare it quite a bit to flood modelling. We're going to go through a challenge where we build up a hydrodynamic model trying to solve a problem. And as we move through building that model, we'll work through what the astronomical tides are, how the climate, weather, and the ocean can affect the ocean water levels, spectral wave modeling, and then we'll wrap things up. Now, this presentation, I'll be talking for about 40 minutes, is really a taster to coastal modeling. Okay, you're not going to go away today, being able to run or build all these things straight away. But what I really want you to take away from this is that you have a better understanding of the scale and the size of the processes that are involved in coastal modeling and how they compare to flood modeling. So we'll be using 2FLOW-FV as a hydrodynamic model and SWAN as the spectral wave model today. It's really aimed at new coastal modelers, flood modelers, and those interested in understanding more about coastal modeling as well, so managers and things. So it's very much aimed at those target audience members. I've really kept the theory to a minimum, but I'd encourage you to go and have a look at this free coastal wiki on the Astronomical Tide and waves if you're interested in knowing more, because we could talk about that for a long time. 2FLOW-FV is the hydrodynamic model we're using today. We'll be basically doing some 2D modeling, but there are lots of options to look at sediment transport and water quality. A lot of the pictures that I'll show you today are 2FLOW-FV results, but we're using QGIS and the free 2FLOW viewer plugin for QGIS. There's a few definitions I'll run through just to start with. Rivers and flood modeling. Okay, a lot of us are used to these types of studies, where we're really interested in how rainfall runs off a catchment and to a lesser extent how groundwater might affect the catchment. As we move downstream, we have estuaries, and this is a region where rivers will start to mix with the ocean. And on the right-hand side, this is Myanmar, and shout out to the Myanmar people. I saw there's a couple on the list of attendees. This is near Yangon. And we have a river system moving up. This is salinity that's shown in the plot. And this is a long section of salinity moving up the river. So we have salt water down near the coast. And this is a 3D long section. And we have fresh water moving down to meet that. I've nominally called coastal the area seaward of the coastline for about 100 or 250 kilometers. And this is where we're actively using the coastal zone, beaches and ports and shipping. Once we move further offshore into the ocean, we're really talking about the deep water ocean and where the global and offshore processes are important. So just keep that in mind. So how do flood models and coastal models affect each other, or the processes that we're looking at? On the left-hand side, I've got coastal processes that might affect how you set up a flood model. Now, the most obvious one that comes to mind is that we're building a flood model down near the coast, and we've got to assign some sort of tailwater level to the downstream boundary. Now, that might be in the form of the astronomical tide, it might be a storm tide boundary, or it might be some static water level that we need to ascertain. If we move further up into the catchment, the ocean effects don't really play a role, so they're not as important, but certainly down near the coast they are. The river mouth morphology, so if there's a lot of sediment built up at the river mouth or in the lower parts of the river, that can lead to issues or increases in flood upstream, and that can be important. And also the interaction of salt and fresh water. So as per the Myanmar picture I just showed you, we can get these interactions that change the density of the estuary. However, if we're looking at big flood events, the fresh water tends to move down and basically blast all of that out to sea. So they're not so important. Now, in terms of river processes that affect coastal modeling, freshwater river flows can be important in the estuary area, but flood flows don't really tend to affect the ocean at all, really. The volume of water out in the ocean compared to what's coming out of a river is very limited, and any increases in level are very localized to around the river mouth. What rivers are important for are delivery of coastal sediments, okay, in the sediment budget, and also nutrients that can be important for fisheries and a whole range of other ecological processes offshore. Just a few applications of coastal modeling that we can look into for our projects. On the left-hand side, we mainly have water levels and current related activities. In the middle, we have port structures and sediment transport and dredging. And on the right-hand side, it's more environmental considerations, aquaculture, ocean outfalls, and to an extent, animal migration and salvage and rescue. The big difference that we see when we start to model in the coast and the ocean is related to scale. So in terms of temporal scale, that is the time frames that these things are occurring over. In flooding, we tend to have events that might happen for hours or days, you know, and it's usually the type of time frame we're looking at. As we move into the coasts, we're looking at hours to years, and as we move off into the deep ocean, days to hundreds of years, these scales or these processes can occur over. In terms of the distances that these things are happening over, you know, in the catchment, we're worried about things that may be meters to kilometers and, you know, rarely bigger. In the coastal area, meters to thousands of kilometers, and ocean, we're looking at global scales. So we need to think bigger when we're moving out into the ocean. In terms of the processes that we need to look at and include in our models, rainfall is no longer the star of the show. You know, it's been out in the limelight there for flood modeling, and once we move across into coastal space, we're not really that interested in it anymore. Sorry, rainfall. What is important though is the astronomical tides and the interaction between the atmosphere and the ocean. Coastal model boundary conditions, we tend to use gridded outputs, or gridded boundary conditions, which you can see on the right-hand side here, which is gridded wind speed and pressure, because of the space and time scales that are being operated on. 3D effects often need to be considered, so you can get, you know, the situation where the water's moving one direction at the surface and then it's moving the other direction at depth, but also density. So the effect of salinity and temperature and how they move water around can also be important. And rarely do we need to look at salinity and temperature in flood modeling. And the last one, ocean waves, okay, generated by wind and breaking on the shore, is not something that we typically look at for flood modeling. All right, so to work through these processes, we've got this modeling challenge. We've had a client come to us and say, oh, we've had this event occur at our tide gauge. And so this black dashed line represents an actual real water level measurement that occurred during a real storm. And we're going to build a model to try and match that observed level. And this is Urangan from the 24th to the 30th of January 2013. Now, where is this? Well, it's over on the east coast of Australia. I'm where that blue dot is. And as we move into Hervey Bay area, and we move right into where the Urangan tide gauge is. So in order to try and reproduce this water level, we need to firstly develop a model domain. Then we're going to run that model with the astronomical tide only as boundary conditions. Then we're going to increase our inputs to the model and start to include meteorological influences, primarily air pressure, mean sea level pressure, and wind. And as we build these models, I'm going to walk you through the various data sets that we need to build the model, but also the physical processes that we are trying to represent in a model. So step one, develop the hydrodynamic model. Now, you might be a bit surprised, but really coastal and flood models, you know, they're not that different really. We still have to demarcate where the model boundary is. We still need to make decisions about that. We then have bathymetry, okay, or topography. We then need to have a computational mesh to solve the equations of momentum and mass conservation. Similar to a flood model, we have boundary conditions, okay. In a flood model, we're usually looking at flow rates or water levels downstream. In the ocean, okay, water level variations are important to capture, and you know, we rarely put flows in except maybe at a river location. Then we need to make some decisions around, you know, bed roughness models and turbulence and viscosity, just like flood modeling. And we also need data points. calibrate our models to. And so in our study area, we have the Urangan tide gauge, which is the one that we've just been looking at with that observed measurement. And we've also got a location at Bundaberg, which is just slightly up the river. That's important for something I'll discuss. So this is a 2-flow FV mesh. And what we do is, you'll see it, you move with quadrilateral elements and triangular elements. So it's a flexible mesh. We move from quite low resolution offshore where the water's deep into finer resolution as we come on shore. We spend quite a bit of time demarcating certain parts of the mesh so that we can define the right sort of size mesh cells that we want for the water depth and the processes. And as we move further inshore, we increase the complexity as well. So that's a very different process from flood modeling, where you might just set a set grid resolution for the whole model. We're really trying to upfront save a lot of time, and that's because of the scale. You know, if you tried to model at 10 meters cell size all the way out to the other end of the ocean, your computer would explode basically. And we just don't need to model at that resolution out in the deep water. We need to apply bathymetry, and in the same way we do to a flood model. So the data comes from a different place. There's soundings out in the ocean from Admiralty charts. It might be analog charts or digital online data services. In estuaries, there may be soundings that have been collected or cross sections that we can use. And if we're moving out of the tidal range and onto the land, for example, looking at storm tides or tsunamis, then LiDAR can be important. So for this study, I've been very lucky in that there's some online data. I've grabbed this JEBCO 2020, which is quite good in deep water. And in the shallow water, I've moved in and grabbed some of this Elvis data. So this is all freely available online data. Again, if you're in a different part of the world, there may be some online data for you, or you may need to source some for yourself. Now, I'm going to talk about putting the astronomical tide onto this model that we've just built. But before I do that, I want to walk you through what the tides are and why they're important. So the astronomical tides, they drive the water levels and the currents, you know, out in the ocean, in the tidal ranges of the ocean largely. They are responsible for the intertidal areas, so mangroves and mudflats and seagrass. And they can be really important ecological areas. So where we have very large tides, you have a larger area of intertidal, and you can have small tides where you have less. And that can affect things like how long the mudflats or the intertidal area is wet for. If there's only one high tide or one low tide a day, that can affect the types of ecology that grows there. The tides can modulate the wave attack on the beach, the size of the waves, and can be responsible for erosion and deposition. And at the kind of pointy end of the stick, when we're starting to try and protect our coastal infrastructure or design how high it needs to be, we need to have a look at how high the tides get. We also, from a navigational perspective, and that's what the dredge is doing here, is we need to understand when the tides goes out, how much water is under a ship, and is it going to be stuck there? Now, most flood modelers will have some experience with the astronomical tidal plane charts. So you need to go in and have a look at things. And this might be where the story ends for you. Essentially, they're just, apart from the HAT and LAT, they are just mean levels that have been derived from tidal observations. And I'll go into this in a bit more detail. So the astronomical tides are long period waves that are driven by the differences, and that's important to note here, the differences in gravitational attraction across the planet as our rotating Earth moves. And that's mainly responsible because of the moon and the sun. So the moon and the sun affect the gravitational forces on the Earth. The time of the year and the changes in the moon's orbit and Earth's orbit, the Earth's axial tilt, all affect the tides. And so each of these different gravitational pulls, the moon and the sun and the Earth's rotation, can be all broken down into a series of partial tides called tidal constituents. These forces are influenced by the continents and the ocean bathymetry and the Coriolis force, and tides differ greatly across the world. So this animation on the right-hand side here is the main moon constituent, the M2 constituent. The white colors are higher areas of water elevation and the black is lower. And what we tend to see is that these waves set up as standing waves in the ocean basins, and they rotate around nodes or amphidromic points. And so there's a lot of different tide heights and tide directions across the world. Now, if we look at the tides on the eastern side of Australia and the western side of Australia, these are both tide predictions. And you can see that there's some really different behavior going on. First thing you might notice is that on the east coast, in our study area actually, we get a lot higher amplitude, so the height of these tidal waves. And they're also semi-diurnal, that means every sort of 6 hours. Now, when we go down to the bottom, you see very different, the amplitudes aren't as great, and the actual periodicity, how often they occur is quite different as well. So these numbers up here are these different components of gravity that I was talking about, these different gravitational waves that move around the oceans. And so if we have a look at the top picture here, we can break that water level prediction down into a series of constituents. And so we start with the moon, okay, and here's the effect of the sun. And when they're in phase, so full moon or new moon, we get a resonance, an amplification of the tide. And when they oppose each other, we get a reduction. So your sort of spring and neap cycles. As we add more of these gravitational features, if you watch down the bottom, what we're doing is we're adding each one of the constituents, and you're starting to see, something that resembles more of the tide that we observe at the coast. So the ocean water level that you see offshore is really a combination or an addition of all of these different tidal constituents. How do we know what these are though? Well, we can put tide gauges in on the coast, okay, and they might be there for 20, 30 years. And when we take those water level measurements, we can analyze them and we can pull out the different wave periods and wave amplitudes for these different constituents. So that's why it's really important that we have these monitoring stations around the country. If we go over to Western Australia, it's quite a different story. Okay, the actual M2 constituent doesn't do a lot, and some of these diurnal, the K1, O2, O1 constituents do more. So that's a little bit about the tide and how it works. What I want to talk about now is how we might go about getting some of this information into a model. Now, our period that we're looking at was at the end of January. Okay, this time when our challenge is being investigated. So what we do is we run the model for a month for January 2013. That allows the water to slosh around a bit in the model and warm up. Then we need to source and apply astronomical tide boundaries. Then we're going to calibrate it to the available points that we have. In terms of tide data, we've grabbed some gridded tidal predictions. We have also got tools to do this if you're trying to do it yourself, but there's global tidal models that you can get this information from. Now, why we need to grab these gridded data sets is this picture here shows a long section of water level pretty close to my boundary. So I've got a boundary that moves along here, and it's a sloping water surface boundary. At one end of the boundary here, we've got water levels of about 0.9, and at the other end, we've got values of 0.5. So that water is sloping all the way along there, okay? And that's the way that the astronomical tides work. If we change this from being in the X direction, so at the moment it's in meters along the line, to time, and we look at a point, you can see that over time for the whole of January, that point there is moving around like the tide. And if we took another one here, it would be similar but slightly different. Now, I'm going to show you some model results. What we're showing on here is the water level from the tide, and these are the tidal currents. And this is the blue is the model results, and the red dashed line is the predicted tide. at Urangan. So same as those predictions I showed you before from all the constituents. So I'll play through that, I'll just step through. And what you can see here is that as the tide comes in, okay, here the water level's going up, the velocities are moving in towards the coast, and then we get to the top of the tide, and then we move back offshore, and we have our ebb tide, and water moves away. And what this allows us to do is we've got a pretty good match down here at Urangan, but if we wanted to look at tidal currents or tidal water levels anywhere away from that point, we can be reasonably confident that they're looking okay. This is the astronomical tide calibration at Urangan and also Bundaberg. So the blue is the model, the red is the predicted tide, okay, so just the gravitational forces. And if we go to our challenge, we can see that the blue line, which is the model tide, is not really anywhere near the black line, which was the measured water level. So even though we've done a really good job of modeling the tide, okay, in the top here, we're still missing something. And so there's a bit of head scratching going on, not sure what to do or what it is. So we need to have a bit of an understanding of what could be causing this process. I'm going to talk you through the climate, the weather, and the ocean, just to give you an understanding of the scale of the processes that we're looking at, and some of the things that you might need to consider for a coastal modeling project. Now, the ocean and the atmosphere are intimately coupled together, okay? They need each other, they drive each other. And a lot of our climate and weather is driven by the differential heating of the Earth. So at the equator, there's an excess of heat. To reach equilibrium, that heat moves away and moves towards the poles. And essentially this redistribution of heat drives atmospheric circulation. We have Coriolis deflection in both hemispheres, which leads to a tendency to have trade winds, okay, in the mid latitudes, and down in the in the subtropical areas we have the trade winds. In the mid latitudes we tend to have westerly winds that occur. Now, as all of this air is moving around, it essentially pushes the ocean and can affect the ocean circulation. And then we have storms that are embedded in these larger scale systems that occur as weather events. So this animation here, I'll just get rid of my here, just shows the air temperature and the wind speed. So this is from the Earth Null School. Awesome, go check it out. This is just from a few days ago. And you can see the wind speed at the surface moving around. We have all these embedded storms, and this is happening all the time. If we take that a bit further and look at the ocean, okay, so this is the temperature. If we then look at the ocean, we can see that, let's give it a moment, that there's also currents in the ocean. So what's being shown on the screen right now is ocean currents. And they are also redistributing heat, mixing water, and having eddies. In some places, those eddies lead to upwelling and downdwelling and differences in sea surface temperature. And so a lot of these ocean circulation processes can increase or decrease weather events. So just if you take anything out of these slides, just be aware that there's a lot more happening on a ocean basin and synoptic scale than just your flood catchment that you might need to be aware of. So how do we go about actually including some of this stuff in our models? It's a bit overwhelming, right? Well, we're actually really lucky in 2021 in that we have a lot of data that we can use both from the meteorological perspective, but also from an ocean modeling perspective. And so we have these global weather models that we can go and freely download data from. I'm going to today grab some mean sea level pressure data and also wind speed. If we were looking at a 3D assessment, which we won't cover today, we might need to get things like air temperature and radiation. There's also models of the ocean, and these can be important for the 3D structure of the ocean, but also wind waves, things like the East Australian current. And so we need to sometimes grab salinity and temperature data, which I won't cover today as well. So this is awesome. You can go on to get a Copernicus account and go and download some wind data and pressure data, and then you get it. And then you can drop it straight into the two-flow viewer. Here's our model domain. We can add this in. And so what I'm about to show you here is actually the gridded wind speed, surface wind speed. The colors are the mean sea level pressure. And so we have that data, it extends far enough to cover our whole model domain. And so we can apply that. And if we look at a time series of wind speed, which is blue, and the pressure in red, you see there's a bit of a weather event potentially occurring around the 25th of January. And so maybe that's what's going on with our water levels. Back to the model, we've gone in and we've applied those wind speed and pressures into the model as a boundary condition, and that's applied across the surface. What I'm showing up the top here is the wind speed, which is the white arrows. The contours are the water level values. And down here, we have the predicted tide, which is red, which I was showing you before. Nothing's changed there. The blue is the model, tide plus surge, and the black is the same measurements from our challenge. And so if we play through this, what we'll see is that the wind is pushing the water down into Hervey Bay. And this is known as a storm surge. So both the wind and the pressure is really pushing that water down. And when you look at tropical cyclone modeling, these sort of storm tide events can be fairly important. So back to our challenge, how are we doing now? So again, the black is the dashed line, the measurements, the model with the wind and pressure in there is the blue. And look, I'd say, you know, that's pretty good. That's pretty good. You know, it's a lot better than where we were. And so we can go in and we can write up our report if we're trying to match the peak level, and happy days. So what happened? Well, there was a passage of a storm that created a storm tide at Urangan. And even though we had a really good astronomical tide calibration, it wasn't enough to reproduce what was actually being measured at that location. And so we did need to include wind and pressure for this site. In other places, it might be important to include 3D ocean effects where you have different types of stratification. But for this case, it was okay just to have these inputs. So because we did such an awesome job and we're all happy and everyone's happy, the client has actually come back to us and said, all right, well, we've actually had a bit of a doozy here. And during the same storm, there was a fishing boat out and it capsized and sank at this location. And we need to have an investigation, understand what the wave conditions were at the wreck site. So maybe we can, you know, try and avoid these types of things in future if we can forecast the waves and see what's happening. And so we've been asked to reproduce a significant wave height and the peak wave period at this location. Now, what I want you to do is take off your two-flow FE hydrodynamic hat. So up until now, we've been talking about water levels and currents and hydrodynamics. To solve these questions around waves and wave propagation, we need to move towards how to model wind waves. And we do that via spectral wave modeling. So wind waves are a complex combination of different waves in the ocean. If you look at this picture here, you know, you don't have one particular wave moving from one direction. You have many different waves that overlay on each other to give you this kind of chaotic looking picture. And they have different directions, heights, and speeds. They're generated in quite a complex process by shear and resonance by the wind. But essentially, the longer and the harder that the wind blows over a given area of the ocean, known as a fetch, the larger the waves will grow until an equilibrium is reached. And there's two main types of wind-driven waves in the ocean: sea waves, which are sort of locally generated waves, and then we can get swell, which can be generated by local storms, but can also travel vast distances, thousands of kilometers across the ocean. So why are ocean waves important? Well, they act to distribute energy across the ocean. So as I said, you could have a storm that's down in Antarctica. The waves from that storm can end up in Alaska. And those waves can have a tremendous amount of energy. So this is Port Fairy recently, where some waves threw a few rocks around. And look, this shouldn't be all that surprising to people. These rocks aren't all that large anyway. The waves are extremely powerful and can throw much larger things around. They are responsible for, in a part to upper ocean mixing. But where they're really important for us as engineers and scientists and managers in this space is around structural design. Okay, am I going to have my structure destroyed by waves at that site? Navigation is also important. So ships might go, off their normal direction just to go around large waves that are not nice. Also for coastal structures to protect ports from large waves. They're important for sediment transport and coastal morphology, so they drive a lot of that process, and also important for recreation. Surfers come to mind there. So in terms of estimating the wave conditions, what we need to do is build a spectral wave model. And what this does is it models the evolution of wave energy across the surface. They look at wave dissipation, so how waves might be affected by white capping or frictional effects, wave generation by the wind, interaction between different waves, wave setup, and there's a lot more that you can do with them. We'll be investigating the coastal wave model SWAN here. It's built by the Delft University of Technology. You can go and grab it from there if you want to, and it has a lot of good local coastal shallow wave processes in it. There's also offshore wave models as well that can be used further offshore. This is a bit of a plug for our newly freely available SWAN GIS tools. So these will be ported with the TwoFlow QGIS plugin. They're not actually the SWAN model, but they're tools to help you develop the SWAN model domain. So this is a TwoFlow FE model here. The red grids are the SWAN domains that we're building. So we have a large model, we have a smaller one, and we're nesting into smaller models here. So anyone who's used SWAN before, this can be quite a cumbersome process to do this. So what the SWAN GIS tools will do will help you to build your control files, wave spectra, nesting, bathymetry, and wind files. So if you're interested in any of that, please let me know, and we can send you an example and some doco to try it out. This is just the tool in process. So go to the model builder, brings up this process here, panel, sorry. Got the model folder, the configuration. The key thing here is that we can build our domains dynamically with GIS polygons, so we can draw those in and modify things like the rotation and the length of the cells. We put our bathymetry in, and the same wind data and wave data that we had before from the Copernicus site, we can drop into here. So this will just show you quickly, we can come in here, we can change the rotation of the grid. See the rotation in the gridded box there. We can reverse the rotation, okay, and we can change the cell sizes. I'll just skip forward a bit on this, and we can also have nested grids as well. So I'll just show you quickly. So you can have nesting, and what the tool will do is it will actually generate all of the files that you need for that. So it helps a lot. In terms of actually solving the dilemma of this capsized ship, what we need to know is what was the significant wave height at a particular point. And the significant wave height is the average of the highest 1/3 of the waves that we see at that site over a particular period of time. And the wave period, peak wave period, and that's the time between successive wave crests for the waves that had the highest energy in the wave spectrum. And these can be output directly by SWAN, and there's lots of other options. What's quite nice is that we can also bring that into the TwoFlow Viewer plugin. And so up the top here, we've got, again, the wind speed during this event. So this is at just before 25th of January, 2013. We've got our site here that we're interested in, and the colors are the significant wave height contours. So just the first thing that's interesting, right, is that you've got the winds coming across, and this is quite shallow up here, so there is some shoaling or breaking of waves in that area. But you can see the sheltering effects of the island, okay, as you move down here. Down on the time series, in blue, we have the peak wave period, which is on secondary axis in seconds, and the black, which is the significant wave height at this point. And so if we play through this, I'll sort of jump to different parts of the storm. So as we move across, we start to see the wind moving further from the north, or the northeast, and the way that island is shading the Harvey Bay is different. If we go further into the storm, to the peak of the event, you really see the wind starting to drive the waves down, and the actual wave height and the direction of attack changes as well, in that the waves are coming from the north and they're affecting greater areas as well. So in terms of solving the mystery of the boat and what the wave parameters were at that location, we can pick them off the time series here. So we're talking about a 4-minute significant wave height, okay, and around 9 seconds, which is at the lower end of the swell wave period spectrum. So again, very quick run through of some spectral wave modeling, just to give you a taste there. If you're interested in knowing what else you can do with them, you can integrate waves and hydrodynamic models together. And so you can apply those wave outputs from SWAN to two-flow FE or another hydrodynamic model, and they can affect the currents and the water levels. Waves can be really important for sediment transport modeling, and you can also run a wave and hydrodynamic model together in two-way coupled mode. And if you're interested in seeing an application of that, have a look at the Mooloolaba structural design example from this previous AWS webinar. So just to wrap things up. So really, I know I say it, but the flood and ocean models really aren't too different. Okay, we're modeling water moving around. What is different though, very different, is the scale and the processes that we need to include. Okay, noting that we didn't even go to 3D today. And so the water levels and the currents, due to the astronomical tides, they vary across the globe in time and space. And the currents and water levels at the coastline, aren't just due to the astronomical tides, because the ocean and the atmosphere are intricately linked to each other. We also often have to include the effect of the weather. So often each year, the water levels that you see at the coast will exceed the predicted astronomical tide due to these things we call tidal residuals, which is contributions of ocean processes, climate and weather on top of the astronomical tide. And ocean wind waves are also important to consider in coastal space that we don't consider in the flood world. I guess finally, models can help us to extend our knowledge away from the measurements. Okay, so we had those calibration points, but because we built those models, we can have some confidence that the water levels and the velocities away from those points are reasonably well represented. They also allow us to model scenarios and designs as well. Calibration is really important. Obviously, not always possible, but where possible, you should really try to calibrate your model to give yourself more confidence. And there's some great models out there, and there's some great data sets out there. And ultimately, it's how we use them. And I guess just a final closing remark. Again, if you can take anything out of the presentation today, I hope that you have a better understanding of some of the coastal processes that occur, the scale, and how we need to be aware of what's happening, just away from our river system if we're in the coast. So thanks very much for that. Again, Michael's going to answer all your questions, and I'd just like to say thanks again to the Australian Water School. If you haven't checked it out, go have a look at the website and all the previous webinars. It's a really great resource. So thanks very much.
Great, Mitchell. That was absolutely Wonderful. We enjoyed that. I did hugely. I mean, to go from global to local like you have, and yet not tie us down in vast amount of detail. You've only got this 40 minutes, and you did that with aplomb. You did that so well. Thanks so much for that. It is incredible. I mean, I'm a surfer from way back. To watch those wave diagrams, I just wish I had a handle on them when I'm on the board. You know, where's the next hit going to come from? A good surge here? Beautiful. No, that was fantastic. And Michael, hammering away on those questions. I'm watching them going back and forth. Why don't you take us through the next few minutes and what you think we should do next? So up to you where you want to head to from here.
Yeah. There's a common theme running through a few questions, Mitch. I was wondering if you could comment on. Quite a few people have asked how we might integrate a coastal model and a flood model to look at a combined storm surge and flooding impacts inland sort of questions. How often would we do that? What sort of model configurations would we use to do so? All those sorts of things have come up about that linkage or interaction between the two. Some comments on experience or examples around that.
Yeah, often in the tidally affected areas of a river, we want to include some coastal processes, so we can go offshore a little bit and use the tidal predictions offshore to really come into the coast. There's increasing benefit, I suppose, to having combined modelling systems, and I think that over time they will be more prevalent. There's still value in having specific models to answer specific problems. Like if you've got a flooding issue and you're running a flood model, that's good. Often you don't need to consider what's happening on the coast, or if you are, you can run the coastal model separately and apply the boundary conditions downstream. Having said that, there's these models I've showed you today. There's no reason why we couldn't go up the river, have the floodplain incorporated, have the structures all incorporated if that was important for the study, and have a fully integrated flooding and coastal model. Where you need to be careful about that, though, is that always comes at a cost. And so if we're trying to run a flood event, we may be restricted in how fast the model can run through such a large system, as opposed to running them separately. So I don't know if you had anything more to add to that.
Yeah, I think the message is that it can be done, but everything comes at a cost, and that's usually a computational cost. Two-flow FE, for example, certainly has all the structures and things that are needed for bridges and culverts and whatever to simulate those inland flooding processes. But it comes back to me to what are we using the models for? What questions are we trying to answer? And therefore, how do we need to configure models? Do we really need to look at detailed coastal processes and inland flooding processes at the same time, or can we break it up? And those sorts of questions are really beginning of study questions that need to be addressed. There's another question here, which is the SWAN model here, was it in stationary mode or in stationary mode that you presented?
Yeah, it was in stationary, so dynamic, changing meteorological conditions. So the wind and was changing over time.
Yeah. Another question similarly was, HS and TP are sensitive to return period. How long a return period is specified for this challenge, or what's this challenge about?
I guess the concept of having a return period assigned to this is it was one event. Okay, if we needed to try and assign a return period, so return being the average likely period that it might occur or be exceeded by, we typically run a very long set of simulations over a long period of time to look at that. So I wouldn't say that the HS and TP is related to the return period. I'd say that we have a storm that's occurred. It's got a certain wind speed. It's caused water levels, and it's caused wave heights and periods, and they can be basically referenced relative to how often that event might happen at that location. Yep.
There's another question here. I've seen during the presentation that ERA5 were used to force the model wind and atmospheric pressure. How confident are you with using ERA5 in terms of its accuracy?
Look, I think what wasn't done today, just through time, is that you always want to try and ground truth this stuff. So if you've got measurements of wind speed and mean sea level pressure on the ground at your site, you can compare the global model data to what you have. So that's what I'd recommend that you do. ERA5 seems to be great. There are, for this particular site, it might not be so good for other sites. And so it's good to look at a range of data and to ground truth that data.
Yep. Another one, any comments on approaches and modelling limitations relating to breaking waves and breakwater design in terms of energy dissipation?
Yeah, I think if you're getting right down and dirty into how the waves may affect a structure, with the spectral wave modeling I've showed you today, you can get key wave parameters like wave height and wave period, and you can put those into coastal engineering guidelines to pull out, likely stresses. But if there's a specific structure that you're looking at, you might need to go to like a CFD type model and run the waves through that. So hopefully that helps with that question.
Yep, no worries. There's a question here which I can probably answer. How can we do wind and storm surge in one model software for the Arabian Sea along the Pakistani coastal area? We've actually done that in Tuflo FE, and we have a model of the Arabian Sea and the Gulf of Oman, and we look at those things right now. We're doing some work for the Abu Dhabi Environment Agency on that, but certainly the model extends out there and can be used for those sorts of processes that Mitch has been talking about today, along the similar lines that Mitch has outlined. Mitch, a good question for you. Are coastal processes different on the east and west coast?
Yeah, they certainly are different. One of the contributors to that different, I guess we're talking about Australia specific here, is the difference in the astronomical tides. We have a lower, when I say lower tide, down in southern parts of Western Australia have very low tides, but then if you go up to the Kimberley region, you have these massive tides. The exposure of the Western Australian coastline to the Indian Ocean and Southern Ocean is different, so you get different types of waves that approach the coast. On the east coast, down around Brisbane, we have big sandy beaches, and waves tend to drive a lot of that. We have, as we move north, they've got the Great Barrier Reef, and they tend to dissipate a lot of wave energy. You get mud flats and things like that. So fundamentally, coastal processes are very different in a lot of different places, and the vegetation, the wildlife, the sediment types that you get there will be reflective of those coastal processes.
Yep. An interesting one here, Mitch. How many tide constituents should we use to produce a reliable tide prediction? Yes, that varies depending on where you are in the world.
Yeah, exactly. So some places can be incredibly complex, and you might need over 100 tidal constituents to accurately model the tide, because there's a lot of interactions happening as the tidal waves move across shallow water. We based ours on 8. There's not really any answer. What you want to do most likely is to go and grab your water level recordings from a site, and you can understand what the different constituents are for that site, and that should show you reasonably quickly how important the different constituents can be.
Yep. Okay, and then one that's related to the first question that we talked about, which was the interrelationship between catchment or land-based processes around flooding and coastal processes. A really good question here. Do you have any recommendations or experience in modelling entrance morphodynamics for coastal lakes and lagoons, storm events? Would you need to integrate models together, e.g. X-Beach and Delta?
Yeah, look, the only experience that I have is looking at Tuflo FE's sediment transport module morphological integration with Tuflo. And in that case, you run the hydrodynamics and it scours out the bed, and sediment transport can move. I haven't personally done a lot of like longshore, long-term sediment transport, but I can see that there are advantages of doing that. So, but they are quite, I guess, unless you're doing longer-term processes, you might be quite separate exercises that you do.
Yeah, I think the short-term events can be handled in a model like two-flow FE with morphological, dynamic bed changes in time. And we have icols in Australia intermittently closing and opening lakes and lagoons, and they're all about that sort of process. And that's an example where I think you really do need the catchment modelling to play a role, because often water levels will build up in these lakes inland and then drive that process of erosion once the initial breakage occurs of the sand dune or whatever it is that's closing the mouth. So that is an example, I think, of overlap, but it's typically short-term events we'd look at in that sort of modelling. And one of those reasons is, again, because there's a large computational overhead associated with modelling morphological processes over extended periods. It take a long time to do that. We would therefore look at longer term models like XBeach or similar empirical models.
Hey, what do you reckon? We leave it at that. We're up to nearly the hour mark. What do you think? Everyone, don't you glean so much from hearing a couple of professionals toss ideas back and forth? I do. It's just a fantastic, it's an incredible medium to play with. And we're talking to people from 50 countries all at once, just with the graphics and the audio all happening together. Thanks so much, Mitchell, Michael. We do hugely appreciate you taking the time to do this today. And thank you everyone for participating in the discussion like you have. It's been a fantastic hour. I never cease to be, anyway, I won't run it on anymore. That's enough of that. It's been great. Recording link, we're going to email it to you. We'll upload it to our website and YouTube channel. Watch it for freely with your colleagues after, for as long as you want. There's hundreds of webinars up there now. And there'll be a short 1-minute survey popping up at this webinar's conclusion in just a minute or so. It'll come up automatically. And if you don't get to see it, put your phone on that QR code down there, and you'll be able to go straight to the survey. I think that's it. Any final comments, Mitchell, Michael?
All good for me, Trevor.
Thanks very much, and thanks everyone for attending. It's great to see you.
Indeed.
Yeah, that's a great pleasure, and the comments coming through in the chat line right now, highly appreciative of the time today. It's been fantastic. Look at those on-demand courses, webinars, and live courses all coming up there. Stay on the website and get your friends to come to the website, and you'll see what's going on. It's huge. Well done. Thank you, everybody. Thank you, Joel, and Australian Water School. It's been terrific. See you, Mitchell. See you, Michael.
Thanks, everyone.
Catch you next time. Bye for now, everyone.
Thanks for watching. Subscribe by clicking the link below and click on the notification bell to stay up to date with new releases. For the latest in significant, innovative and critical advances in water science, technology and management, subscribe now. To build your skills, enhance your technical knowledge and learn from leading experts in water, visit theaustralianwaterschool.com.au and discover our online training courses, both live and on demand.